Welcome to the SaberRD online training course. This series of fast-paced videos will quickly teach you the full power of the SaberRD simulation environment. In this section, we look at test automation. The RD in SaberRD signifies robust design. Robust design makes system performance immune to variations in design technologies, component parameters, manufacturing processes, and operational conditions. Experiments are an important component of the robust design capabilities within SaberRD. Once you know how to create experiments, you will be ready to apply robust design tactics such as design optimization, sensitivity, Monte Carlo, worst case, stress, and fault analyses. Experiments are test setups. Once created, they become part of the design, making it easy to replicate results. They can be duplicated, shared, and modified. They are easy to construct without the need for writing code. We will illustrate how to construct experiments by analyzing this switching power supply. It is a boost configuration that steps up 5 volts to 12 volts. A behavioral pulse width modulator model outputs a digital signal that controls an ideal switch. It produces a sawtooth waveform which drives one input of a comparator. The other comparator input is connected to an internal error amplifier. A Type 3 compensation network is used to stabilize the loop response. We will create 2 experiments. The first will power up the circuit, running a time domain analysis until the output has stabilized. Several of the circuit signals will be automatically plotted. The second experiment will start at the endpoint of the first domain analysis. A series of current impulses will be applied to the output to see the response of the design. The average output voltage and ripple will be measured after each pulse has been applied. Construction of the first experiment starts by going to the Simulation tab. Instead of selecting an analysis from the pull-down, Experiment is selected. This makes an adjacent pull-down appear. New is selected. The new experiment is given the name Startup. 3 new sections appear. The experiment pane lists the new experiment. A blank canvas in the middle with a tab labeled Startup is where the experiment commands will reside. A new tab along the top labeled Create appears. The experiment operations are chosen from this palette. Construction of the experiment starts by selecting the transient operation. A line appears on the canvas along with a set of default properties. The canvas is not a free-form text editor, though some properties can be changed directly on the canvas. The value for time end is changed to 30 milliseconds, and the time step is changed to 1 nanosecond. More detailed control of the operation is accomplished within the Properties pane. All the operation's properties are listed. For this example, the signal list is changed to gather all signals. The operations line on the canvas correspondingly changes. The next step is to determine which signals are to be plotted. Selecting Define Graph creates a container for the signals. We change the generic label of the container to Important Signals. A plot signal operation adds signals to the container. The indentation shows it is within the scope of the container. Clicking on the question mark chooses the waveform to plot. We choose the only simulation from the list, and Vout is chosen by browsing through the list. 2 more signals corresponding to the inductor current and error amp input are added with plot signal operations. The experiment is executed. Upon completion, the graph called Important Signals is listed in the Results tab. Double-clicking it shows the 3 signals that were specified by the experiment. It is time to create the second experiment. Under the Simulate tab, Experiment is selected from the pull-down, and New is selected from the adjacent pull-down. It is given the name Impulse. Again, the experiment will be using a time domain analysis. A current pulse will be applied to the circuit and the response measured. The circuit must be in a stable state before applying the measurements. But there is no need to go through the startup sequence again. Instead, this experiment will start at the endpoint of the previous one to save simulation time. The start time is set to 30 milliseconds. This was the end time of the first experiment. Time step is changed to 1 nanosecond. End time is changed to 50 milliseconds. Run DC analysis first is changed to No. The initial point file is changed from DC to TR. The endpoint file and plot file are both changed to TR2. Signal list is changed to All Signals. All these changes are reflected in the command line on the canvas. Like the previous experiment, a graph called Important Signals is created. Variables can come in handy when creating experiments. A few will be created for this one. A variable is created with a Set Calculate button. Its label is changed to time start and given a value of 30 milliseconds. It is dragged to the beginning of the experiment. A variable for the width of the pulse is created. A variable for the end time is created and set to twice the pulse width. Now we can go back and insert these variables into the time domain analysis command. The next step is to set up the current pulse. We can see from the schematic that it is connected to the output and given an initial plus value of 0 so as to have no effect during startup. An alter command is selected. It is used to change the delay of the pulse to coincide with the start of this experiment. It utilizes the time start variable. Another alter command sets the width of the pulse. Both alter operations are placed before the time domain analysis. The magnitude of the current pulse needs to be set. This time, a parameter sweep operation is used. It is placed after the alter operations. Dragging the time domain analysis over this iterative task nests it inside. The indent shows it is properly nested. The parameter to sweep is pulse. The variables of the parameter sweep are set to begin at 0 amps, end at 10 amps with 1 amp steps. Next, the measurements for the average voltage and voltage ripple are created. A measure operation is placed within the parameter sweep. The plot file to read is TR2. The signal to read is Vout. Log is set to yes, so the data is gathered into a table. An average measurement is chosen. Its label is changed. The measure needs to be made near the end of the pulse to allow for settling. 2 more variables are created for the measurement start and end times. They are placed in the X-range property of the measure. Another measurement is created for ripple using the amplitude measurement. Pass-fail indicators are added by selecting the test operation. The calculator can be used to set the test, or it can be typed in. Tests are created for both measurements. A test is made to see if the average value is above 12 and if the ripple voltage stays below 80 millivolts. Executing the experiment runs a series of simulations corresponding to the parameter sweep, and an experiment report is created. Opening the report shows a nested set of values corresponding to each step of the parameter sweep. Green values indicate a passing measurement, red a failing one. These results can be exported as an Excel spreadsheet. Plotting the important signals displays a family of curves for each of the runs. Selecting the signal label for Vout allows us to bring up the member attributes from the local menu. Among the many functions in this panel, selecting Hide All and dragging the mouse across the members shows each one individually. Plotting a measured value versus a sweep parameter can provide valuable insight. This will be accomplished with a few more operations. First, a measure operation is placed outside of the parameter sweep. It is set to read the time domain plot file. Because it is reading a family of curves, this measure will produce a waveform. Notice that the icon changes to indicate this. Like before, the average value and ripple are both measured. A container for the waveforms is created. An entry for each measure is placed inside the container. A solid line style and circle symbol are selected. After the experiment is executed, the waveforms are available for display in the Results tab. Here is the finished impulse experiment. Though it was developed for a relatively simple configuration of this boost converter, it can be reused on more complex versions of the design, perhaps using more detailed models such as a nonlinear inductor, an IGBT for switching, and soft start for the PWM. This concludes this section of the SaberRD online training course. To download a free student version of SaberRD, go to the Synopsys website. To further your understanding of this material, go through the lab exercises found at the link listed in the description of this video.